Over to you.
Hello, everyone, and hello to everyone watching this video. My name is Heath. I'm from Pennsylvania State University, and today we are going to be talking about our capstone project. My teammates include Colin, Harsh, Will, and Fife. We worked with Jim throughout the semester on a very exciting project which solves a real world problem. So let's dive right in. Our goal is to review the final results of the synthetic data generator, which is the project that we worked on, while we also examine our approach from the very start of the semester. We had roughly 15 weeks to work on this project. We all know the dynamic. Industry has real world problems, and students, they've got the energy, they've got the enthusiasm to solve them. But as it is illustrated in this comic strip over here, there is a distinct wall between us. Companies cannot share proprietary data sets due to strict privacy laws and IP protection. This leaves students working with toy data sets. And let's be honest, it's not fun sometimes, and it's also misleading at times. They don't reflect the complexity of the real world, which limits the value of their education. So the core question arises that how do we tear down this wall without breaking the law? Our solution is a synthetic data generator that answers the question, unlocks specific value for three key groups. First, for ISSIP specifically and the industry in general, it creates a scalable mentorship model without the legal risk. It even allows companies to test drive potential new hires by seeing how they can handle complex quasi real data. Second, for universities, it strengthens corporate relationships by absolutely removing the IP hurdles that typically stall these collaboration for months and even years sometimes. And finally, for students like us who are in our senior year, junior years, in the modern economy, we have to work with data. AI is here. All the businesses run on data. We need hands on experience with messy, complex, really annoying industry data, not just textbook examples to be truly ready for our careers. And on top of this, according to Gartner, by 2026, 60% of the data that is used in the development of AI and analytics projects will be synthetically generated, which affirms the problem and shows a real need for a synthetic data generator, which will be solving so many more problems and have real world application right now today. So what was our project? Our project addresses these barriers to industry academia collaboration by generating synthetic data that safeguards privacy while preserving the statistical utility and realism of original datasets. Over to Harsh.
This slide summarizes the five key requirements that define success for our project in terms of data quality, security, and scope. First, on the privacy side, our synthetic data can never reproduce a one-to-one match with any records in the source dataset, and we remove all PII in the line with ISO 2889-2018. Second, for the data quality, the numerical statistics of the synthetic data like means of key columns must stay within plus or minus 5% of real data. Third, for utility, any model trained on synthetic data has to be within 2 percentage points of the accuracy achieved on real data. Finally, in terms of the scope, the tool must support at least 3 case studies in healthcare, education, and agriculture. Risk management. On the risk matrix, you can see each risk moving from red region into the green after mitigation. R1 was low fidelity. Our VAE originally deviated more than 5% from the real data. We added automated hyperparameter optimization with deep hyper, which brought the deviation from 8.2 to about 3.1%. R2 was privacy leakage. To prevent synthetic data from reproducing real records, We implemented nearest neighbor duplicate check. After that, we observed zero duplicate records. R3 was adoption. We were concerned that sponsors might find the tool too hard to use, so we created a sponsor playbook and automation script that reduced the adoption risk to low with documentation and continuing as ongoing work.
This risk matrix might make you ask a lot of questions on what a VAE is or how did we go about getting from the start. So Colin will now explain our entire pipeline from the very start. Over to you, Colin.
Thank you, Heath. So from the beginning, with synthetic data, which is a very wide topic, we narrowed down our focus on synthetic data to tabular data sets with both qualitative and quantitative data, and wanted to focus on how synthetic data can enhance privacy in industry academia collaboration, where sometimes there's data that can't be shared. With these goals in mind, the approach that we decided to use was a VAE for the actual data generation part of the project. We had a couple of options available, such as GANs and LLMs. However, VAEs work the best with quantitative data and can also handle qualitative data as well with a little bit of pre-processing. Thus, with our beta prototype and our initial implementation, we used Python with only freely available packages to make sure this stays open, such as PyTorch, TensorFlow, scikit-learn. And with our project, we were able to generate sort of a test synthetic data set for one of our selected case studies, the student data set. With this proof of concept, we saw that we're going in a good direction. We can generate synthetic data set to enhance privacy in these sort of collaborations. But the direction that we wanted to go next was looking at scalability across a number of different data sets from a number of different sources. Because if we have a solution that works just on one data set, it's hard to argue that this is a good solution for everything. So that was our next focus on this project. For a final prototype, our main goal was taking this specific solution we had and making it a more general solution, showing that for different industries, for different data sets, this is something you can use for this goal of privacy and utility. To do this, our VAE needed to be fine-tuned for different data sets, not just our student data set. With differences in data sets such as size, number of features, and types of features, such as whether it's mostly a quantitative data set or has a lot of qualitative data as well, we saw that our beta prototype only worked efficiently on just a portion of these. So for our final prototype, we decided to implement DeepHyper, which is an optimizer for some of our parameters for our VAE. With this, DeepHyper was able to find a best fit for a lot of these parameters, such as the latent dimension or the number of iterations to run for our VAE. Along with the scoring function, to tell DeepHyper how good of a guess that it made on these parameters, we were able to show that this initial implementation we had could be scaled across different data sets. Here on this slide, you can see a couple of sample visuals, which show an initial scoring for different data back on the previous slide, which show an initial scoring here in these first two slides, which show the correlation of the data as well as the similarity to the original data set. As the optimizer ran iterations, we showed that this base implementation was able to work well on any sample data set that we gave it. The second two visuals, here we show the difference in performance of models built on this, because a big thing with synthetic data, of course, is building models. So one of our key testing scores was how well does a model built on the synthetic data work on the original? And this here shows the difference in performance based on synthetic and original. As our optimizer ran and found better fit for these parameters, it got much, much closer, down well within our target goals.
So going on into the results, before evaluating performance, we first needed to confirm that our pipeline could handle different types of real-world data sets. To do this, we tested, as Colin mentioned, across three distinct data set types representing education, healthcare, and agriculture. Our data set for education and health was from the University of Irvine Machine Learning Repository. The first data set, which was the student performance data set, was a mixed type that included large number of categorical and numerical variables. This data set represented the most complex modeling challenges because variational autoencoders VAE typically struggle with data sets that contain many categorical variables. The second data set was the UCI heart disease data set, which contained sensitive clinical information. This data set represents one of the most realistic use cases for synthetic data, which is enabling medical data sharing without exposing private health records. And finally, our third data set was from the USDA agricultural data set, which was mostly used for regression tasks. This one was purely numerical and allowed us to test the pipeline's ability to preserve continuous variable relationships and regression utility. So our findings show that the VAE and the hyperparameter pipeline delivered high fidelity, preserved privacy, and produced synthetic data that achieved model performance comparable to real data models. We evaluated fidelity and privacy utility across all three case studies, and the VAE performed strongly across the board. First, fidelity improvement substantially after introducing our hyperparameter optimization to our final prototype. The mean deviation on the student data set dropped from 8.2% in the beta prototype to just 3.1% in our final prototype, which brought us comfortably within our 5% target, which we had. Second, privacy was a complete success. Across all data sets, the pipeline generated zero duplicates of the original data, and every synthetic record had a non-zero nearest neighbor distance. This confirms that the synthetic data is fully anonymous and does not leak identifiable information. And third, which I will follow up more on the next slide, we assessed utility, which essentially is how well a model trained on synthetic data performs when tested on real data. If you can go back to the scatter plot shown, the scatter plot shown here is not one from our three case studies. It was generated on a separate medical data set with more data points. We just used it to clearly illustrate the trend that shows that model predictions from synthetic trained data follows the same overall pattern as predictions from real trained data. And finally, this chart shows that our final system met all fidelity and privacy requirements and achieved strong utility performance across two of the three case study. First, you can view from our VCRM that for fidelity and privacy across all three data sets, the system passed every fidelity metric. The student's data set mean deviation dropped to 3.1%, heart was at 4.4%, and farming at 2.9%, all comfortably within our 5% requirement. On the privacy side, we, as mentioned before, we recorded zero duplicates across all data sets. This confirms that our synthetic data is not leaking real data points and remains fully anonymous. The most important section of this table is the bolded utility rows, which represents our utility matrix for each case study. For the heart disease data set, utility passed with a very small drop in accuracy, 1.5 percentage points. This is a strong result, especially for a clinical data set, and shows that the synthetic data preserves the pattern needed for decision making. On the farming data set, we also passed utility with the R squared score decreasing only marginally from 0.78 to 0.75. That is a 0.03 difference, which is negligible for regression task. Where we had our issue, as I mentioned before, was on our student data set, where the AUC dropped from 0.91 to 0.88, which made a 3-point gap, which was more than our 2-point threshold that we had. But we know that data set containing large categorical variables make some issues for the VAE in modeling. And finally, just to talk about our budget, this project was entirely software-based and focused on developing a computational pipeline. We utilize open source tools like Python, GitHub, PyTorch, DeepHyper, scikit-learn, which carry no licensing fees. Computation was performed using existing university provided resources and personal student computers. Therefore, the total actual expenditure of the project was $0, which is well under our budget allocation.
Our work followed a 15-week agile schedule. In phase 1, we focused on emphasizing with ISSIP and defining the problem. meeting with a sponsorer and selecting 3 datasets and logging in the statement of work. For phase 2 was our ideation and beta prototype phase. There is where we built the first VAE, discovered that it failed the fidelity requirement, and then intentionally replanned the schedule to integrate the deep hyper optimization loop. Finally, in phase 3, we focused on final prototype and validation. We ran full HPO, executed the VCRM test on all 3 case studies, and prepared the white paper, presentation, and the poster. In practice, this phase also included a short deliverable period, cleaning up the GitHub repo and writing the sponsor playbook so that the ISSIP and the future teams can actually pick up the tool and use if we are done.
Now, to talk about our future directions, as mentioned before, we had to focus on just a part of the synthetic data problem overall. So that leaves us with a couple of places that this project can go in the future. For starters, something that we had talked about before in some of our meetings is the possibility of a closed system that will train models on data, identify potential weaknesses in the model, and use synthetic data generation as a way to generate more input for these models to learn from these sort of weak points and grow stronger overall than they could have just on the original data. Another potential direction to move on to is exploring more complicated types of data. As mentioned, we mostly focused on tabular data with qualitative and quantitative types of data in that data set. However, there's many other types of data, of course, such as images, which have plenty of real-world applications across many different industries and would be an interesting direction to move on to when looking at synthetic data generation. And finally, one of the most important parts of this project is the scoring, because of course, producing the synthetic data is the most important part, but without knowing if that synthetic data set has high usability, high fidelity, it's a bit difficult to work with it and fully trust the results gained with it without being able to measure how good the synthetic data set is. So as such, while we are happy with our scoring data set, this is something that should be continued to look into to make sure that it can be applied to as many data sets as possible.
Now, as we wrap up our presentation, we want to give a thank you and acknowledge those who helped us, such as Dr. Subramanian and Dr. Noti as well. And finally, of course, a big shout out to you, Jim, and to the ISSIP team for giving us the opportunity to work on a project that not only challenged every single one of us, but also try to bridge the connection between students and the industry. And so if you have any questions, I want to thank you for listening to our presentation. And if any questions, we would love to hear them.
Well, first of all, great work, team. It's amazing to me what you were able to accomplish in a really incredibly short amount of time. And I hope you had some fun and learned a lot. And I'd like to ask each of you a question, and I'm just going to go in the order that I see your names here. So Colin, for some reason, you're at the top of my list. So I'm going to start.
All right.
So what is the most surprising thing you learned about synthetic data or this use case during this project? And then I'd love to have you say a little bit about your thoughts on how you think AI is going to impact your career in the future.
So to start with, the surprising thing about synthetic data, I would say, is about just the variety of data out there. Of course, there's many different types of data, like we mentioned, qualitative, quantitative, image, sound. But beyond that, the types of formats that they come in, and even if they come in the same format, the types of considerations that you have to take into account. Like I mentioned, we had a number of different data sets that we had, which were all the same tabular data sets with qualitative and quantitative data. Yet even then, one solution couldn't quite work the same on all of them. We had to put in a lot of work, even on these very similar looking data sets, to get good results. So I would say that was the most surprising thing for me. As for how I can see AI coming into my workplace, going into computer science, it's a big consideration for me. Of course, there is some fear in the mix with it because a lot of companies are looking at how AI can maybe partially or fully automate some of the coding process. However, even up until now, I've gotten to see some of the benefits that it can bring. Even right now, part-time, I work as a research assistant here at Penn State working on embedded systems. And one of the biggest things that I've seen it's been a huge help with is sometimes you need to get some information out of a manual that's thousands of pages long, and you might need this information now, and it's maybe a niche problem, and there's not a lot you can find on Google, but somehow AI is able to identify, this is the information you need, this is where you can find it. And so for the information gathering, it makes this process way easier. And I see that being a huge part in my future career is at least the gathering of information so I can focus my time on building a product rather than having to spend a lot of time looking through unrelated information.
Great. Yeah. Big productivity booster for sure. Next on my list is Harsh. So Harsh, what was the most surprising thing you learned about synthetic data, and how do you think AI is going to impact your future?
Honestly, the most surprising thing was how real the fake data can feel. Going in, I thought synthetic data would be kind of watered down and not that useful, but when we actually ran the test, the models trained on the synthetic data were only about 2% worse than model trained on real data. So the big surprise was you can completely protect people's privacy and still get the data that's good to make solid decisions. And for the second question, I see AI becoming a co-worker rather than a replacement. As an industrial engineer, a lot of my work is improving systems. AI gives me ways to test ideas quickly with simulations, synthetic data, and optimization before we touch the real system.
Great. Thank you. Thank you, Harsh. Hey, you're next on my list. What was the surprise, and how do you see AI impacting you in the future?
Sure. Going off of what Harsh actually said, I also believe that the most surprising thing was how good fake data can be, and also learning that data utility is significantly more difficult to replicate than data privacy for synthetic data. Initially, going into this, I was like, okay, it's going to be more about how I can keep the data secure so that there's no one-to-one matching. But we found out that bringing it down to that 2 percentage point was the one task that took the most of our time. And to answer your second question, again, going off of what Harsh said, that I believe that working in tech specifically as a computer science student, recently there was this claim by a Claude software engineer that software engineering is going to be dead. And I somewhat see that happening already. That I think rather than being an individual contributor, you're kind of going to be like an orchestra conductor. So what the barrier today to building things is so low that you will have so many swarms and swarms of agents working for you. And your sole job is going to be, okay, this AI now is supposed to talk to this agent, is supposed to talk to this agent. And my job is to only make sure that the pipeline keeps running all the time. And I'm pretty excited for it.
Great. Yeah. I think you're all going to be CEOs of startups and managing hundreds of digital workers, and you're, instead of getting jobs, you're going to be acquired by other bigger companies. That's what I think, similar to what you said about the orchestration. So Will, what was surprising, and how do you think the future is going to look?
So for me, apart from our topic, investigating synthetic data and the value it brings to industry and academic collaboration, for me, what impacted me the most in this project was our approach that we used to build and evaluate a machine learning model from end to end. That for me was the most impactful part because it was something I was interested on that I feel that if I didn't have these great teammates, it would have taken me many more years and time to learn, which I would say is the most impactful part that I learned, which transitions to how I see AI impacting in my career as a graduating industrial engineer, which what an industrial engineer does is optimize process. And now in the era where we're living, AI automation agents, workflows, machine learning models are the best tools to optimize efficiency in industry. So my goal is to be able to get familiar with these tools and be able to use them and apply them in any industry and scenario and be able to do a high scale AI transformation for many industries. That would be My career goal, yes.
Great, great. That's fantastic. So Fife, what was surprising to you about synthetic data, and how do you see AI impacting your future?
Um, I saw the surprising thing for me, just so similar to how Willin had talked about, was really the utility and how to really get the synthetic data to look to be viable. You know, it was definitely a lot harder than how it sounded. Oh yeah, just create synthetic data. But no, it was definitely a lot harder, and it surprised me even in that process of creating it, like in a slide that we showed earlier, a little bit of our graph, just even that broke it down, but we really broke it down a little bit more. I learned about what a hyperparameter was and optimizers and things like that, which definitely are things I need to know, which moves on to how I think AI will affect us. I think it's something that I need to get more on. You know, it's definitely going to dominate the field. Even just here at our school, they just started a new major called AI engineering. So people are getting onto that. So it's definitely an opportunity here to get a little bit of a head start to know, okay, maybe these are some things that they'll start using in the future that I can apply to myself and hopefully have my own startup company. Who knows?
Well, I celebrate all five of you. Great job, team. And if I can be of any assistance in the future, please don't hesitate to reach out. I've gotten to know you all a bit in this online 15 weeks of exciting exploration. Thank you so much for all you've done to help ISSIP. It's an exciting journey. We're at the beginning of this exciting journey, and it was great to share it with you all. So thank you so much. I'll get the blog post posted. If you want to put your digital certification on your LinkedIn, do that. If you run into any trouble, let me know. And again, please do stay in touch. I look forward to following your careers and see. I do hope many of you become CEOs of startups and get acqui-hired by a big company like IBM or Google or whatever. Okay, team, thanks so much. Have a great
You, Jim, for your
Have a great.
time
Thank you,
as
Jim.
well. Thank you so much for your mentorship. It was lovely working with you.
have a great holiday and New Year. Bye for now.
Thank you very much, Jim.
Thank you,
Bye.
James.